Good morning. Myself, Dr. Shaila Dinkar Apte. Today, we will continue with IIR filter design, that is part 3. Under this, we have already considered in part 2 the details of Butterworth filters. There are two other category of filters called as Chebyshev filters and elliptical filters. So, we will see the details of this already established filters in the analog domain. So here we go. This is the book that is published with Wiley India publication. You can go through this book for further details. So first we consider another type of filter that is called Chebyshev filters. Uh, Here there are two types. We can have Chebyshev filter type 1 and Chebyshev filter type 2. In case of type 1 filter, it allows a small ripple in the pass band and there is monotonic nature, monotonically decreasing in the stop band. And in type 2 filter, it allows small ripple in the stop band and it is monotonic in the pass band. So what is the difference between Butterworth filter and Chebyshev filter? We want to see. In case of Butterworth filters, it is maximally flat in the pass band and monotonically decreasing in the stop band. So no ripple is allowed in the Butterworth filter. So the disadvantage that we got is it is requiring higher filter order. But the advantage is it is maximally flat in the pass band. Now in Chebyshev filter, we can allow a small ripple in the pass band, either in the pass band or in the stop band, depending upon whether it is type 1 or type 2. And by allowing a small ripple in the pass band or in the stop band, we are in a position to get smaller order of the filter and we also get the smaller transition width. This is attractive part. But at the cost of what? At the cost of higher computational complexity. As we understand, there is nothing like free lunch. If we want to achieve something, we have to sacrifice on the other thing. So this is the corresponding characterization of the filter. In this case, this Tn represents Chebyshev filter. This is a polynomial of order n. So these polynomials can be calculated, they can be expanded. T0 x equal to 1, then T1 x is equal to x, then Tn plus 1 x is equal to this. So using this equations, iterative equations, we can generate these polynomials. Okay, these can be generated recursively, but these are difficult to calculate, as you can understand. And these polynomials are supposed to be used in the denominator and then the filter is to be designed. So in case of this particular filter, the roots of the polynomial occur always between -1 to +1. Now in case of odd order for the filter, Tn0 is equal to 1, and in that case we get magnitude response is equal to 1 at omega equal to 0. So this is the response that we get for n odd, and for n even, Tn0 is equal to 1 and hence h of 0 mod square is 1 plus 1 upon 1 plus epsilon square, which comes here. So this is the response for even even order of the filter. Now here you see that there is a ripple in the pass band, and because there is a ripple that is allowed in the pass band, this epsilon appears. This epsilon is related to the ripple in the pass band. So 1 upon 1 plus epsilon square to 1 is the range for your pass band ripple. The squared magnitude response is written like this. The magnitude response for odd n and even n is shown here. This is for type 2 filter. In this type 2 filter, the ripple in the pass band is 0, but ripple in the stop band is allowed. And because of this, again we get the smaller transition width, and again we can get the smaller order of the filter. So let us see how the filter order can be calculated. So this is the equation for filter order. We will not go through the derivation of the filter order. We will just remember that this delta 2 is supposed to be the attenuation in the stop band. Epsilon is related to your passband ripple, right? So and delta 2 is equal to 1 upon under root of 1 plus delta square. This delta is supposed to be some parameter which we are assigning for deriving this equation, because this particular value comes often in the derivation equations. Let us see how the design will be carried out. So suppose we consider type 1 filter with the specifications given here. 1 dB ripple in the passband. The passband edge frequency is 0.2 pi and the attenuation at 40 dB of 40 dB at zero point 0.8 pi. So this is supposed to be the stopband edge. This is the cutoff frequency, passband edge for the filter. So omega c is 0.2 pi, omega s is 0.8 pi. So we calculate delta 2. Delta 2 is 40 dB as it is given, so 0.01. So we can calculate delta from this equation. So delta comes out to be 99.99. Let's go ahead. So 10 log to the base 10 of 1 plus epsilon square is equal to 1. So from this, you can calculate what will be the value of epsilon, because it is given as equal to 1 dB. So we substitute the value and get the epsilon passband ripple. Then n can be, order of the filter can be calculated using this equation. In this, we have to substitute the value of delta 2, we have to substitute the value of alpha, and we have to substitute the values of omega s upon omega p. This is stop band edge frequency, this is pass band edge frequency. So just substitute the known values and you get the order as 2.89. In case of Butterworth filter, we got the filter value as n is equal to 3 point something. That is why we had chosen n is equal to 4. Now in this case, the filter order is reduced to 2.89, and in this case, we can just use the filter of order 3. Now for this, here the specifications are not so stringent. If the specifications are stringent, then the filter order can be something like 80, 90, and in that case, there will be a larger difference when you calculate the filter order for the Chebyshev filter. Now let us see another category of filters, that is called as elliptic filters. Now, in case of elliptical filters, what they do is they allow the ripple, small ripple in the pass band. They also allow small ripple in the stop band. So what they do is they distribute the ripple equally in all the bands. And this reduces the maximum ripple value, as you can see. And these will have ripple in the pass band. They will also have the ripple in the stop band. So elliptical filters will result in a smaller transition width as compared to Chebyshev filters, and they also will have the smaller filter order requirement as against Butterworth filter and Chebyshev filters. The filters will have both the poles and the zeros. These are not just the all pole filters, these are pole zero filters. So squared magnitude response will be written like this. In this case, this un is a Jacobian elliptical function of order n. So this is quite complex to calculate, but the Jacobian functions, they are tabulated in the form of a table. We can refer to the table and get the Jacobian function calculated, right? So this is the corresponding filter order equation that we see. K is supposed to be the complete elliptical integral of the first kind, and delta 2 against for stop band ripple we can calculate. Delta 1 is the pass band ripple, we can calculate using the value of epsilon that will be specified, or if delta 1 is directly given, we can calculate epsilon and put it in this equation to calculate the order of the filter. Is that right? So in this particular case, we get smaller transition width, we get smaller requirement for the filter order, but we will have to allow small ripple in the pass band, also the small ripple in the stop band. Now, these are the designs that we have considered. Those are for the DT filters, that is discrete time filters. Now, when we design actual digital filters, these discrete time filters will have to be converted to the digital domain after quantizing. So, what are the things to be quantized? We'll have to quantize the input signal, input sample. We'll have to quantize the filter coefficients. And then when we multiply the input with the filter coefficients, again, there will be error. So, what type of errors are generated? we can see there will be error because of the truncation and rounding, because every particular value, input value, will have to be either truncated or rounded up. So there will be some quantization error introduced in that. Then input signal sample quantization will result in the error. Coefficient quantization will result in the error. Product round of error. This arises because when we multiply the signal sample with the coefficient quantization, there will be a multiplication of the two quantized quantities, and the corresponding output will have to be again quantized with the same number of quantization levels. So again, there will be product round of error. There will be scaling considerations also, because there should not be any overflow in the output, and limit cycle oscillations and oscillations due to overflow. So these are the type of errors that we have to consider or discuss or take it into consideration while designing the IR filters in the digital domain, because these quantization effects may change the state of the filter. It may tend to make it unstable. So all these considerations will have to be done before the corresponding system will be designed. Thank you.